Hello. I want to look at a interesting constant and an interesting series related to that constant. The constant is gamma. It's defined as the limit as n goes to infinity of the harmonic series, sum k equals 1 to n, at least partial sum, minus the log of n plus 1. So put it that way. So it's that limit. Pictorially, let's see, we got n plus 1 here and an n there. Why that? Well, it's a little better if we look at the graph. So if I graph, say, y equals 1 over x, there it is. The area under the curve from 1 to 6 will be natural log 6. And if I look at the step function, first with height 1, and then with height 1/2, and then 1/3, it's always going to be at that intersection there. Then this series, or this area, is 1, because the base is always 1, plus then this area, the area of that rectangle would be 1/2, base times height, now be 1/2. This would be 1/3, right? There's 3, 1 over x, this height is at 1/3. This will be at 1/4, 4 goes to 1/4. This will be at 1/5. So this represents the area of this sum h5. So if I subtract the two, you get just that. So we want to know, as n goes to infinity, what's the sum of all those areas? We can do this graphically. You've got, let's look here. If you were to slide over every area, it slides over this way, and it's going to be inside the unit square. Right, so here's part of it. Might as well go up to there. A little blow up. I didn't want to go to infinity. It takes a long time. So this is only, going through h5 minus log 6, sliding those over. But if you go to infinity, everything's going to be under, and so you're just going to get a partial of this area. So you can see the sum is bounded. It's increasing. It's bounded by 1, obviously, the area of that square. It's obviously less. It's around 0.577, something like that. So there's the sum. It can be defined, and I'll put it this way. If we were to look at the limit as n goes to infinity, sum k equals 1 to n, 1 over k minus log n, well, that would be the sum k equals 1 to n minus 1 over k minus log n. And I lost my limit. Let me put it in there. Limit n goes to infinity. This expression, put parentheses. Well, I can add and subtract log n plus 1 inside there. So this will be the limit as n goes to infinity of sum k equals 1 to n, 1 over k minus the log of n plus 1, and then plus these two things, and I'm going to put them as a single log right now. Log of n plus 1 divided by n. Right, so this log minus that log, subtraction on the outside is division on the inside. And then, of course, this goes to 0. I guess I'll do the one more step here. Limit n goes to infinity. I should just call it hn, but I guess one more time. Writing that, minus log n plus 1, and then plus the log of 1 plus 1 over n. And then this term obviously goes to 0 as n goes to infinity. As we get closer and closer to log of 1, roughly log of 1 plus 1 over n will be 1 over n. So as n goes to infinity, this goes to 0. giving this. So this limit, if you only have an n, that limit's the same as this limit. So it doesn't matter which way you define it. They both converge to the same thing, which we'll call gamma. All right, so now for the interesting result. Let's look at integers. We'll start at, say, 3. Well, I could start at 2. So if n equals 2, take all the divisors, including 1 and the number itself, which for 2 are the only two numbers, and divide 2 by those things. So I want 2 divided by 1, because that equals 2. And I want 2 divided by 2, and that equals 1. Now there's no fractional part here, so it's actually pretty uninteresting. What I want to do is find how far is this number to the next integer that's bigger than or equal to this number. And in this case, it's 0. Right? So the next integer that's bigger than or equal to 2 is 2. So that's 0. And the next integer that's bigger than or equal to 1 is 1. So we'll start to get fractions at this point. So when n is 3, I'm going to divide 3 by every number smaller than 3. Did I say all of its divisors? No, not all of its divisors. Every number. So 3 over 1, 3 over 2, 3 over 3. So then this will be 3, 1.5, and 1. So again, 3 is 0 away from the next integer that's bigger than or equal to 3. So do the math. Now 1.5, now that's 0.5 away. 2 is the next integer that's bigger than or equal to 1.5. And then 1, again, is 0 away from the next integer that's bigger than or equal to 1. So I've got these 3 numbers. If I average them, well, it's the sum, which is 0.5 or 1/2, I'll do as a fraction, over the 3 numbers, so that's 1/6, or about 0.167-ish. Okay, so I'm just going to do that with every integer that exists. Actually, maybe I'll do less than that, but I'll do a few more smaller ones here. N equals 4. So 4 over 1, 4 over 2, 4 over 3, 4 over 4. So we get 4, 2, 1 and 1/3, and 1. So I'll just put the results. Now, how far away? You're 0 away, you're 0 away, you're 2/3 away, and you're 0 away. Again, the average then of how far away each number is to the next integer up is the sum divided by the number of integers. So that's 2/12 or 1/6 again. So I'll do a few more by hand, and then we'll get to the computer, I guess. So n equals 5. Now this one's prime, so we'll have a lot more fractions. 5 over 1, 5 over 2, 5 over 3, 5 over 4, and 5 over 5. You always get at least 2 zeros. There's always at least 2 divisors. I could go into the divisors, but that'll just make the video much longer. The number of divisors of an integer, there's a lot of theory on that. But for a prime, there will only be 2 divisors. And so I get 2 zeros. Let me do the fractions first. This will be 2.5. Well, this would be 1 2/3. So it's about 1/3 away. This is 1.25. Do decimals when they terminate, and then 1. So you're 0 away from the next integer bigger than or equal to. You're 0.5 away. You're 1/3 away. And you're 0.75 away. And then you're 0 away. So what's the average? It's going to be the sum. So let's do 1/2 plus 1/3 plus 1/4 divided by 5. This comes out to be, well, I did it earlier, about 0.3167. So just to approximate as a decimal, you can get the fraction easily enough, but I won't do it. So any more good ones? Well, let's start having the computer do it. So let's see. See what I got here. Just jump to right here. So if I look at my earlier ones, what do we have? We've got, well, I'll go ahead and start with 2. Oh, and I'm comparing with gamma. Let me, so this number is going to come up eventually. You don't see it now, that's for sure, but it will come up. All right, so when n is 2, well, we got 0. So, and this is how far away it was from gamma. Well, it's very far away. It's gamma away. Same with, well, 3, we got 1/6, about 0.167. Yeah, well, a little closer. And 4, again 1/6, then 5. Well, a little closer, but 6 will have more divisors, so it goes back down. And you'd expect this operation to never settle down. 7, that's a new prime. It actually went up though. 0.48, that has a lot of divisors. Well, actually, yeah, prime should go up because there won't be as many zeros. There's only 2. And you're always going up to the next integer, right? So we're not rounding. How far are you to the nearest integer? It's how far are you to the next integer bigger than or equal to. So if you're at an integer, then it's 0, but otherwise you have to write it out. So let's see. So let's do 8. A lot of divisors. Some goes down. Well, it turns out, so I can graph these. Let's see, I've got it right here. So here's a plot of the value. So this is 1. I didn't bother to do 1, but 1 would be 0, and 2 is 0, and then 3 and 4 were at 1/6. And then here's 5, and then 6, and 7 and 8. So the average of how far you are from the closest center, it's a little scattered, but not too bad. Oops, let me go up there. There it is. So a little scattered, but not too bad. So this shows the first 40 values where I do that operation. And, well, if you continue, it does settle down into gamma, right? So there, well, it's starting to settle down already. So this is, now it's at 40 right here, or 41 actually. So 41, so the next 40. And then if I go, so that took me to 80. So if I go to 81, I mean, it's still up and down. So is it really settling? I mean, it's a slow convergence. So let's just speed things up. Maybe we'll go to 1,000. I might as well go to exactly 1,000. Now there it is. See, it's already starting to level off. If I go to, say, 5,000, I do that, yeah, 5,000, it's near my limit. I mean, see, so we've very much leveled off here for every value. 5040, by the way, is 7 factorial, and 5039 is actually a prime, right? So there, this last one is a prime number, 5039, and then this next one is 7 times 6 times 5 times 4 times 3 times 2 times 1. But it doesn't matter, no matter what. And if we look, well, I mean, I've got, bigger values here. Let's see. Actually, I think I did both. Yeah, I thought it'd be a little quicker. All right, so what is this? 1,000,001. If I can edit this timeout, there we go. And we can see we're very close to gamma. And I didn't pick a number. I mean, searching for what number is closest to gamma. I also went the other way. If you go the other way, it's 1 minus gamma. So we went next integer up. If you go the fraction minus the integer down, it's of course 1 minus gamma. I should take this out though. I don't care about that. That's easy to show as long as you know the number of divisors as a fraction of the number goes to 0. Right? The number of divisors of n compared to n, that fraction is going to go to 0. So that's why that would hold. But I mean, well, it took a long time. But I mean, I did 1,000,001. Yeah, I'm not even sure if that's a prime or not, but I'll do 1,000,000. I mean, it converges, so there are no exceptions. Once you reach a certain level of decimal accuracy, you're staying at that level of decimal accuracy, and only further on digits can change. So there we go. Yeah, so no matter what 6 or 7 digit number I put here, I'm going to be extremely close to gamma. There's just no avoiding it, because there's a theorem. So I just thought that was interesting, because it sure doesn't seem like it. Let me look. Here's a list of the beginnings. So I have the work here, right? So for 2, you divide by 1, divide by 2. You're at integers. 3. So these are the values I showed, and then here further on, I didn't put this on paper. But well, for 6, don't do that one on paper. But 6 divided by 1 is an integer. 6 divided by 2 is an integer. 6 divided by 3 is an integer. 6 divided by 4 is 1.5, so that's 0.5 away. 6 divided by 5 is 1.2, so that's 0.8 away from the next integer up. So a lot of zeros, and then the average ended up being 0.2167. So here's the average over here. I should highlight it. So that was for 6. And then 7. So the work's done here until I get to 12. Oops, that's 11. Now you can look at 11 too. 11's prime. So there's only the 2 zeros, the first and last. And then every other number. Right, so 11 divided by 2, 5.5, it's 0.5 away. 11 divided by 3 is 3 and 2/3, so that's 1/3 away from the next integer up. 11 divided by 5 is 2.2, that's 0.8 away from the next integer up. Anyway, so they're average 0.3. But you can see from the values I have here, I mean, it takes a while. It's slow convergence, but then no matter what, I have to have a certain decimal accuracy. And then the bigger n is, the more decimals you have to have. And this doesn't prove it. Maybe I chose these specially, but no matter which numbers you pick, I mean, after a certain point, if you average how far away you are from the next integer, after dividing an integer by every number less than or equal to that number, that average converges to gamma. So that's the result. Hope you enjoyed. Goodbye.